Good morning. This lecture addresses applications of propositional logic. We discuss examples and conclude with several exercises from our text that are similar to those that are assigned. Translating English sentences. Example 1. How can this English sentence be translated into a logical expression? You can access the internet from campus only if you are a computer science major or you are not a freshman. Solution. Define the following propositions. A. You can access the internet from campus. C. You are a computer science major. F. You are a freshman. Only if maps to implication. A implies the quantity C or not F. Example 2. Translate the following sentence into a logical expression. You cannot ride the roller coaster if you are under 4 feet tall unless you are older than 16 years old. Solution. Define the following propositions. Q. You can ride the roller coaster. R. You are under 4 feet tall. S. You are older than 16 years old. The quantity R and not S implies not Q. System specification. Translating sentence in a natural language such as English into logical expression is an essential part of specifying both hardware and software systems. Express the specification. The automated reply cannot be sent when the file system is full using logical connectives. Solution. Define the following propositions. Proposition P. The automated reply cannot be sent. P. The automated reply can be sent. Not P. It is not the case that the automated reply can be sent. Not P. Better. The automated reply cannot be sent. And Q. The file system is full. Q implies not P. Logic circuits. Propositional logic can be applied to the design of computer hardware. A logic circuit receives input signals P1 through Pn, each a bit, either 0 off or 1 on, and produces output signals S1 through Sm, each a bit. We have 3 basic logic gates. The first is an inverter and equates to the NOT operator. It's a triangle with a bubble on the end of the pointy end. The second one is an OR gate, and it has a rounded input and a pointed output. And it takes the two inputs P and Q and forms the output P or Q. Finally, we have an AND gate, which has a flat input vertical line and a rounded output line and forms P and Q. Complicated digital circuits can be constructed from 3 basic circuits called gates, shown in figure 1. The inverter or NOT gate takes the input bit P and produces the output NOT P. The OR gate takes 2 input signals P and Q, each a bit, and produces the output signal P or Q. Finally, the AND gate takes 2 input signals P and Q, each a bit, and produces an output, the signal P and Q. So in figure 2, we have a combinational circuit where the inputs are P, Q, and R, and the output is the quantity P and not Q or not R. Example 9. Determine the output of the combinational circuit in figure 2. Solution. In figure 2, we display the output of each logic gate in the circuit. We see that the AND gate takes the input of P and not Q. The output of the inverter with the input Q produces P and not Q. Next, we note that the OR gate takes the input P and not Q and not R as the output of the inverter with the input R and produces the final output the quantity P and not Q or not R. Example 10. Build a circuit that produces the output P and not R, P, the quantity P or not R, and the quantity not P or the quantity Q or not R. Step 1. Create the AND gate where we're taking the major AND between the two quantities. So on the left we have P or not R, and the other input not P or Q or not R. Then in step 2, what we do is we move to the left, backwards, if you will, and add an OR gate for the Q or not R. And in step 3, we continue to move backwards, and in step 4, we complete our exercise as shown. Logic and bit operations. Recall that we had our truth table of true and false, which corresponds to 1 and 0, as we did before, and a bit is a contraction of the binary digits 0 or 1. A bit string is a sequence of 0 or more bits. The length of the string is the number of bits in the string. And we can see the examples of bitwise OR and an XOR in our diagram shown. So now we proceed to some exercises that are similar to those that are assigned. In this exercise, we translate the given statement into propositional logic using propositions provided. 3. You can graduate only if you have completed the requirements of your major and do not owe money to the university, and you do not have an overdue library book. Express your answers in terms of G, you can graduate, M, you owe money to the university, R, you have completed the requirements for major, and B, you have an overdue library book. So I have put these propositional variables and their meanings in the table. G, you can graduate. M, you owe money to the university. R, you completed the requirements of your major. And B, you have an overdue library book. Dissect the statement. You can graduate only if you completed the requirements of your major and you do not owe money to the university, and you do not have an overdue library book. Consider the first phrase. You can graduate only if. Recall from the previous lecture that P only if Q is one of the alternatives for P implies Q. In this case, you can graduate is the conclusion. Thus we form the partial conditional statement implies G. Next, we consider the phrase you have completed the requirements of your major and you do not owe money to the university and you do not have an overdue library book. In this in particular, we note the conjunction of 3 separate propositions, and we form the partial statement. We have the parenthesized with 3 propositions that we don't know yet, that are joined together by conjunctions implies G. Next, we consider the phrase you have completed the requirements of your major and note that it is exactly our proposition R. We revise our partial conditional statement to R and something else implies G. We consider the next phrase you do not owe money to the university and note that it is the negation of our proposition M. We revise our partial conditional statement to R and not M, and something else implies G. Finally, we consider the phrase, you do not have an Overloo library book, and note that it is the negation of our proposition B. We complete our conditional statement to be the quantity R and not M and not B implies G. We present our work in a manner that is easily understood. And you can see that in our tables below. 7. Express the system specifications using propositions P, the message is scanned for viruses, and Q, the message was sent from an unknown system, and logical connectives including negations. So our solution consists of a propositional variable P, meaning the message is scanned for viruses, and Q, the message was sent from an unknown system. We proceed by stepwise. We identify the phrase the message was sent from an unknown system as Q. We identify the phrase it was not scanned for viruses as equivalent to the negation of the message was scanned for virus. So the phrase then is the equivalent to not P. We examine the connective but and determine that in this case but means and. We construct the compound proposition Q and not P. We present our work in a way that can be easily understood. 41. Find the output of the combinatorial circuit. Solution. We label the input lines moving from left to right. The first thing we do is complement R. The next thing we do is find the output of the OR gate, which is Q or not R. Next, we find the output of the AND gate, which is P and the quantity Q or not R. Finally, we complement the output of the AND gate, having the complement of the quantity P and the quantity Q or not R, as we see below.